this part. Here we are looking at the work examples part 2 for refrigeration. So here we have the question. Now, an ideal vapor compression refrigeration cycle that uses refrigerant 134A as its working fluid maintains a condenser pressure of 8 bar, and an evaporator temperature of -12 as saturated vapor. Now, find the system's COP and the amount of power required to service a 150 kilowatt cooling load. So now this is a schematic diagram that I've drawn. Okay, so state point 1 to state point 2 here, as you can see, the refrigerants will goes into the compressor at point 1. So here we can consider as the compressor inlet, and this point here as the compressor outlet. So it undergoes isentropic compression here. Then from this state point 2 here, that is the condenser inlet, and state point 3 as the condenser outlet. So it undergoes a constant pressure cooling process. And then from state point 3 to state point 4, it goes through a throttling process where it goes through an expansion valve. So the enthalpy at point 3 and point 4 should be the same. So and then point 4 will be the inlet to the evaporator, and point 1 should be the exit from the evaporator. So that is a constant pressure heat absorption. So heat is absorbed from the refrigerated space by means of the A as the transporting medium to the refrigerants that is running inside the evaporator tubes. Okay, so here I have a TS diagram. Okay, so point 1 shows us dry saturated. We have point 1 as saturated vapor, and then point 2 to be superheated. That is based on both the pressure, that is the condenser pressure, 8 bar. So what you have to do is you have to look at 8 bar, so you can draw a condenser pressure of 8 bar, and then based on the evaporator of now -12 degrees C that is saturated. So that is the saturated temperature for the refrigerant, or the R134A, in the evaporator. So that is at -12 degrees C. So it is stated that it is saturated vapor or dry saturated vapor. So what you can do is you can just put a line of -12 degrees C with the pressure. Okay, so from your property tables you can check based on -12 for the evaporator pressure. Okay, so point 2 will be superheated, point 3 is the saturated liquid, and point 4 is the liquid and vapor mixture. Okay, so this is the cycle where heat is being absorbed, okay, or heat is being transported by means of the A to the evaporator tubes. And then here another one, that is heat is transferred out from the refrigerant through the condensing tube by means of air as well as the transporting medium to the environment. Okay, so now here the solution. First thing is we have to look at its state point 1. State point 1 is dry saturated, so you can say saturated vapor R134A, okay, at temperature of -12 degrees C. So based on that saturation temperature of -12 degrees C, you'll be able to find the enthalpy at that point, or the pressure, okay, and the pressure as well actually. So H1 will be equals to Hg, because it is saturated vapor. So what you have to do is you just refer to the enthalpy based on subscript G, that is at -12. So you will be able to find 243.34 kilojoules per kg, and also the entropy as well, that is based on the dry saturated vapor refrigerant. Okay, and also you can find out the pressure as well. Okay, then state point 2. Now As we know that at pressure 8 bar and the entropy of 0.93925, where S2 is equals to S1, you will be able to find your enthalpy either directly read from the property tables, or you need to or require to do a certain amount of interpolations for this. So H2, you'll get 273.71 kilojoules per kg. Now what we are doing here, actually we are finding out the enthalpy based on each point. Okay, so we goes from point 1 to point 2, and we start from point 1 this time, because point 1 shows that it is dry saturated, so it is much easier if you were to start from point 1 and then point 2, then to point 3, where the refrigerant is in a form of saturated liquid. Okay, so the saturated liquid refrigerant R1348, so at pressure 8 bar, that is equals to HF. So you can say H3 is equals to HF at the pressure of 8 bar. So you'll be able to find 95.48 kilojoules per kg. And also we know that from state point 3 to 4, it undergoes a throttling process where it flows through an expansion valve. Okay, so since it is a throttling process, so H3 should be equals to H4. So from this, you now have already found out H1, H2, H3, and H4. So then, to find out the mass flow rate of refrigerant, so we know that RE is equals to m dot. This m dot here is the mass flow rate for the refrigerant. That is based from the evaporator. Refrigerating effects actually referring to the evaporator. So you have 0.1 and 0.4. Okay, so 0.4 is the inlet and 0.1 is the exit of the evaporator actually. So from this, then we know that, okay, it is given in the questions, the RE is 150 kilowatts, and these values are here are in kilojoules per kg. So you get your mass flow rate of 1.014 kg per second. Then you can find out the power required by taking work in equals to mass flow rate of refrigerant multiplied by H2 minus H1, that is the compressor inlet and outlet, where power is supplied in order to, okay, run the compressor. So just substitute the mass of refrigerant that you have calculated and with the enthalpy that we have found, then you will be able to find out its work input, that is 30.81 kilowatts here. So and then you can find out the COP. COP is defined as desired output over required input. The desired output is definitely the refrigerating effect or the cooling effect, and the input should be the power input. So here you have the COP for refrigerator with subscript R, not HP. HP refers to heat pump. So you have the rate of refrigerating effect and the rate of work input. So that is your power input as well. Okay, so that will be your COP 4.87. So that is for this section. And actually, these questions here are actually based on diploma levels. So for degree levels, once I have completed all my diploma levels stuff, then I will continue with the degree level. And thank you. And if you liked my video or my podcast, please subscribe and like. Okay, or if you have any comment, you can put in your comment on the comment section below my YouTube channel. Thanks a lot. Bye bye.